Greetings everyone. So today we're looking at linear programming and starting with the formulation of our linear programming model. So what is model formulation? It's the process of converting a worded problem into a set of linear mathematical equations based on what we call a set of decision variables. Now, first steps. We need to identify the objective of the model, which is why we're doing this model, what's the purpose, and the decision variables. So the wrong decision variables will give you a useless model, garbage in, garbage out. So the objective is either to maximize or minimize some outcome. So many models seek to maximize profits, maximize revenues, or they can seek to minimize costs. But it's not limited to those variables, right? We can be maximizing the reach of an ad campaign. So there are many applications, right? But it's either to maximize the outcome or minimize the outcome. Decision variables. Now, in general, a variable represents something that can take on different values. Decision variables are the variables that we are seeking to choose values that will produce the best possible outcome for us. So in relation to our problem, we want to find the best values for these variables in order to get possibly the best profit or lowest cost or highest revenue. And the decision variables are usually the quantity of each product to be produced. So it's usually related to our product mix. So we start off with an objective function. And the objective function states the objective, whether it's to maximize or minimize, and it provides a linear equation to calculate the outcome. Then, after objective function, we have some constraints. Now, these are limiting conditions. It could be the budget that we have, the money that we have available to spend. It could be the time available to get production done. Or it could be some special requirements given, possibly by a customer, that says the minimum or maximum quantity of a particular product to be made, or the minimum content of a certain input. Right? So any special limiting condition is a constraint. All right, let's jump into an example. So here we have a situation where for this company, each table takes 3 hours of carpentry and 2 hours in the painting and varnish shop. Each chair requires 4 hours in carpentry and 1 hour in painting and varnishing. During the current production period, 2,400 hours of carpentry time are available, and 1,000 hours of painting and varnishing time are available. Each table sold yields a profit of $7, and each chair produced is sold for $5 profit. What is the best combination of tables and chairs that should be made so as to yield the maximum profit? Other limitations given: we should make no more than 450 chairs, and we need to make at least 100 tables. All right, so here goes. What is the objective of this model? And it clearly says what's the best combination that should be made so as to yield the maximum profit. So the objective of this model is to maximize profit. So we start by identifying our objective. Now, once we know the objective, we move on to our decision variables. And in this case, it's clear that the company makes tables and chairs. And the question actually says it. What's the best combination of tables and chairs that should be made so as to yield the maximum profit? So our decision variables, we can let them be X and Y. X will be the number of tables to be sold, and Y the number of chairs to be sold. And together we get a combination of tables and chairs. Now, why do I use X and Y? I use X and Y because we are going to be doing the graphical solution next. And we all know that the graph has 2 axes, X-axis and the Y-axis. Now, how do I choose which one to label as X and which one to call Y? Keep it simple. Whichever is mentioned first, I just put that on my X-axis and I label it as X. So each table mentioned first, so tables become X for me, and the other variable becomes Y. Cheers. All right, let's continue. So now that we know our decision variables and we know our objective, we're going to break down the information based on the decision variables. So our decision variables are tables, X, cheers, Y. So starting back from the top, it says each table requires 3 hours of carpentry and 2 hours in the painting and varnishing shop. So carpentry hours, 3 hours for tables, and painting hours, 2 hours for tables. It goes on. Each chair requires 4 hours in the carpentry shop and 1 hour in the painting and varnishing section. During the current production period, 2,400 hours of carpentry time are available. So we cannot exceed 2,400 hours of carpentry time. And 1,000 hours in painting and varnishing are available. So here we cannot exceed 1,000 hours. So the maximum, we'll list them. Then we continue. Each table sold yields a profit of $7. So profit for tables, $7. Profit for chairs, $5. The other limitations, we should make no more than 450 chairs. So number of chairs, maximum is 450. And make at least 100 tables. So number of tables, the minimum is 100. Alright, so now we have the information broken down based on the 2 decision variables, tables and chairs. So we can now proceed. So we are ready to formulate the model. We start with our objective function, and for the objective function we state the objective, which is to maximize profit, and we establish a linear equation to calculate the value for profit. Right, now we know that the most common outcomes are profit, revenue, or cost. So let's go. Objective, maximize profit. Now how do we calculate profit in this case? So each table sold is a profit of $7. So the profit from tables only would be the number of tables sold multiplied by $7. 1 table, $7, 2 tables, 14, and so forth. So since X represents the number of tables to be sold, we can say the profit from tables is X multiplied by 7. Number of tables to be sold multiplied by 7. And that gives us profit from tables 7X. Next, each chair sold give a profit of $5. So the profit from chairs is the number of chairs sold multiplied by $5. Since Y represents the number of chairs to be sold, then the profit from chairs is Y multiplied by 5. So Y, the number of chairs to be sold, multiplied by $5. And that just gives us 5Y. So we now put it together. Objective is to maximize profit, and the total profit is the profit from tables plus the profit from chairs. So that's 7X plus 5Y. So objective function is maximize profit, where profit is equal to 7X plus 5Y. 7 times the number of tables sold plus 5 times the number of chairs sold. Alright, so we are off and running. Next, we need to list the constraints as a set of linear equations or inequalities. So constraint number 1, carpentry hours. So carpentry hours for tables, the total time spent in the carpentry shop for tables is 3 hours multiplied by the number of tables sold. So if we do 1 table, it's going to take us 3 hours. If we do 10 tables, that will take us 3 times 10, 30 hours. Right? So it's 3 multiplied by the number of tables. And the number of tables is X. So that's just 3X. Carpentry time for chairs is 4 hours multiplied by the number of chairs. So that's 4 multiplied by Y, since Y represents the number of chairs. So our total carpentry time is 3x plus 4y. So based on that, we can say the maximum time available for carpentry hours or carpentry work is 2400 hours. So we cannot exceed 2400 hours. That means total carpentry time must be less than or equal to 2400 hours. Cannot exceed 2400. So we can write that as 3x plus 4y. The total carpentry time should be less than or equal to 2400 hours. Right, so that's first one. Second one, painting and varnishing. So the painting time for tables is 2 multiplied by the number of tables. So that's just 2x. For chairs, it's 1 multiplied by the number of chairs, which is 1y. So the total painting time is 2x plus 1y. Putting it together, the maximum time available for painting is 1000 hours. So the total painting time must be less than or equal to 1000 hours. We cannot exceed the 1000 hours. Right, so since the total painting time is 2x plus 1y, we simply say 2x plus 1y is less than or equal to 1000. And that takes care of the second constraint. Next, number of chairs. It said the number of chairs sold should not exceed 450. Make no more than 450 chairs. So that means the number of chairs sold should be less than or equal to 450. What represents the number of chairs? X. Sorry, number of chairs is Y. So we simply say Y is less than or equal to 450. Cannot go over 450. Right, and that's that constraint. The last constraint is tables. Right, and it says the number of tables sold should be greater than or equal to 100. Because we were told to make at least 100 tables. So based on that, X represents the number of tables. So X should be greater than or equal to 100. And now we have our fourth constraint. But then there's another constraint that we're not given, but it is known. And we need to list it in each case. It's a non-negativity constraint. And all that says is the number of tables sold must be greater than or equal to 0. We cannot sell a negative number of tables. And the number of chairs sold must be greater than or equal to 0 as well, since we cannot sell a negative number of chairs. So both X, the number of tables sold, and Y, the number of chairs sold, both of them should be greater than or equal to 0. And that's our non-negativity constraint. Now once we have that, we now have our model completed. So the model says, maximize profit, which is equal to 7x plus 5y, subject to the following constraints. So we have 1, 3x plus 4y is less than or equal to 2,400. That's for carpentry hours. 2x plus 1y less than or equal to 1,000. That's painting and varnishing hours. Y less than or equal to 450. Maximum number of chairs. And x greater than or equal to 100. Minimum number of tables. And finally the non-negativity constraint. Now you'll notice that I have 2x plus 1y. And some people might wonder why I write 1y. And technically it should just be y. Because in algebra we don't write 1y. If it's 1, we simply write y and that represents 1y. But for emphasis, I'm putting the 1 to make sure that everybody stays on track. Right? But if you write y, you're good. Because that's actually the correct way of writing it. Alright, so having said that, we're closing off this one, and the next video we'll be looking at solving this model using graphs. So the graphical solution for the model. Alright, so in the meantime, thank you for watching. Please like the video, please subscribe for more content, because we keep the content coming, and if you have any special requests, please put it out there and I'll try to see if I can accommodate. Alright, blessings and all the best.